Okay. Then let me switch back here. And then I'll project my slides here. Okay. Can you all see the screen? See my slides? Thank you. So last time we talked about the basic elements for designing a convolutional neural network. We briefly go through some other models, but we focus more on convolutional neural network because that's gonna be the main model, main type of model used for EEG decoding. And when you design a model, you not only have to have a good knowledge about all the components in the network, it's also important to gain some experience of parameter tuning or or to try different design of a neural network so that you can kind of feel how the data can be processed by a neural network. So here I like to introduce this playground, the TensorFlow playground. This is where you can build a neural network, uh, use and process these toy data so that you can have you can and you can have a quick training on your model and see how it perform on the toy data so that you can gain experience quickly about how parameters affect in the model learning. So let me do a demo for you. So I'll switch to the playground here. Okay, so this is how it looks. So here, the panel contains a lot of things. Here you have data, and here you have uh, features. So these data, they are 2D, some kind of 2D data, and you can see the distribution like this, and it's different colors showing the class label of each data sample point. And you can choose the feature you like to use as the input of the network. So it can be x1, x2. So that's just the basic coordinates of each data point. Or you can have some higher order things like x1 square, x2 square, the product of x1 and x2, and even sine x1 or even sine x2. And here you can construct the structure of your neural network. You can choose the hidden layer, the number of hidden layers you like to have. So the maximum is six. But for this kind of data, I think you don't need a too deep structure to process. Otherwise, it will make the computational time longer. And here, this is the epoch. Epoch means how many iteration you like your neural network to update. So with more number of epoch, the model will learn for a longer time, and and learning rate controls it how fast it updates. So it can be so a adequate adequate selection, adequate choose of learning rate is really important. You don't want your learning rate to be too fast, otherwise it will skip over the optimal point in the hyperplane. But if it's too slow, it will make your training too long. So that's not practical. So it's very important to choose the proper learning rate. And the activation function makes significant effect on your training result. So choose the proper activation is really important as well. And regularization is is something probably we not mentioned last time. So regularization is a way to constrain the learning of your model. So when you're doing model fitting, this is a good way to avoid overfitting it um, because it includes some penalty like L1 or L2 norm of your parameter so that they cannot fit too much to the data. And regularization rate controls the regularization. So this is the regularization type. You might want to have L1 norm or L2 norm. The L1 norm will make or will increase the sparsity of your parameter. So it tends to make your parameter to be one or zero like that. And L2 norm tends to smooth your parameter. So it tries to make the parameter not too different from each other. So this is regression rate and the problem type, classification or regression. So it depends on your data. If you want to do classification, you have this kind of data you can choose. And if you do regression, then you can see now the color of the data uh, has a gradient like this. So it's no longer the discrete uh, color label like this. Okay, and besides, we have the ratio of training to test data. So this is about how you like to split your training and test data. If you want to have more data for your model to learn, you probably want to increase the ratio of training data. And adding noise would be also a good way to avoid overfitting because in real world there's always noise in your data, so you don't want to put your model to learn some very clean data. Sometimes the adding some noise would be better for the test performance. And batch size, it will change the size of batch putting into your model uh, at each epoch. So that during within the epoch, so it's like the size of the chunk of the data you give to the model to learn. So let's give a try. So say we have this distribution. You have one class that's the outer ring and the other class like the inner circle. So let's see if our model can find a boundary to separate the inner and outside class. So let's make a smaller model first. Okay, give it a try. So you can see it works very well. So it quickly finds a very nice boundary and make the training and test loss both very small. So let's see if we modify this network by adding more layers. Okay, let's go to sixth layer. So now you can see the training gets lower, and actually the test loss goes very large, as well as the training loss. But soon, okay, you can see suddenly it finds the way and get to the optimal very fast. But we do, but it did take us more epoch to converge to this. So that's the kind of a trade-off. And what else can we do? Let's try some other model like this, the spiral one. So you can see the distribution kind of complex. You can see one class going this and the other class going this. So the boundary would be very complex. You need to create a spiral shaped boundary in order to make a good separation. So let's see if the previous model works well for this. At the beginning, it's not going to the right direction. Okay, so it's hard to estimate how much time this model would get to start converging. It might not ever converge. So let's just stop it here and start by reducing the size of the model. Okay, so it's kind of converging, but if you see the background color here, it seems that this model struggles to find the boundary between these two paths. And you can see some jittering here. That's because um, th- that's because um, it's kind of getting approached to a local minimum, and it's not a stable optimization. So you can see the test performance like this. Okay, so perhaps this is not working. So let's see if we can improve this by adding more features. So through adding the square terms, now you can see it can create some curving boundary within the data space. So previously we see the straight line boundaries, but now using the square terms we can get curving boundary. So what if we add sign terms? Because sign terms seems to be very good for spherical distribution. So let's try again. Okay, so I'll stop here. So actually, I can take hours playing with this. This is really interesting. It's always relaxing to see the model uh, is able to learn from the data and create some boundary that works well for separation. Well, let's try regression. One regression case here. Perhaps just pass this one. This one looks more complicated. Let's do something like this, maybe another layer. maybe hyperbolic tangent. Let's see. Okay, so you can see now our boundary kind of emerge. So the model is not creating a boundary to separate the space. It's trying to find a way to fit the color of these samples. So you can see it's creating this grid-like uh, distribution that fits this model distribution, the data distribution. Okay, so I highly recommend this for you to spend some time playing with this and using your creativity and your intuition to the data and the model to create some very nice model fitting. Okay, any question so far? 好，那这个就是一个可以让你去测试，用不同的方式去设计一个简单的模型，然后去用一些简单的资料，然后去看模型怎么样去 fit 你的资料，然后它可以让你就是看这个 training 的过程，它怎么样慢慢去贴近这个资料，然后你有很多不同的选项，那就是对于这个设计模型的经验累积会很有帮助。So okay, let's get back to the slide. Okay, so let's have a quick recap on the multimedia because in the following of the in the rest of the class, I will talk about different models for classifying EEG, and most of the models were developed based on developed for classifying multimedia EEGs because that's the one of the most well-known type of EEG data that we can play with. So previously I mentioned that you can see some symmetric pattern when you imagine one side of your body, like the left hand or right hand. So you can see the spatial and spectral pattern difference when you do left hand or right hand multimedia. 好啊，就是我这边再复习一下我们的这个动作想象的意义区。那当我们在想象左手在动的时候呢，我们会看到就是它的这个空间分布，还有这个频带能量的分布会有一些变化。Okay, so here you can see when you move your left hand, when you imagining moving your left hand, you will see a decrease of power around your right hemisphere. That's around C4 channel. And in the spectrum, you will see a, let's see, okay, you will see the C3 and C4. So if it's left hand imagery, you can see there is power, high mu rhythm power at C3 and low mu rhythm power at C4. Okay, so here I say mu rhythm instead of alpha rhythm is because when we talk about the frequency band around 10 hertz around motor area that it's mu rhythm. It, although they share the same frequency range, the pattern is slightly different, and it's representing different function of your brain. So here I say this is mu rhythm because this is from C3 and C4 that's around the motor cortex. 好，那这边我们可以看到，就是当你在想象左手的时候，左手在运动的时候呢，你的C3在左边，C4在右边。那 C3这边的话，你可以看到你的 power 比较强，mu rhythm 的 power 比较强，就是10赫兹这边。那跟阿法频带是一样的，但是因为是在讲这个动作区域的这个频带能量，所以我们讲的是 mu rhythm。然后它其实在时间上的波形是有点不一样的，我们之前有介绍过。那这边就是，所以当他在想象左手的时候，你可以看到说，左边这边能量那么强，但是右边这边能量就比较小。哦，所以这边我们可以看到一个power 的 decrease 在这边。那如果在想象右手的话呢，你就会看到相反的情况。那现在变成是 C3这边的 power 会下降，好，所以对应到这个曲线就是下降。那 C4这边是能量还是高的，好，所以这就是那个 motor imagery 的 pattern。Okay, so you can see if it's right hand imagery, you will see the opposite distribution from left hand, and you can see the C3 at the left hemisphere have a power decrease, and that's also shown in the power spectrum. It's mainly happen in the mu rhythm around 10 hertz. So besides mu rhythm, the beta power also has some significance when you try different uh, motor imagery. So it comes along with the mu rhythm. If mu rhythm decrease, then the beta will also decrease. So this is corresponding to the ERD and ERS we've introduced. So event-related desynchronization or event-related synchronization. So at the time I said desynchronization actually refers to the power decrease in your EEG. So that's what you see here. When you have left hand imagery, and you can see the C4 ERD desynchronization. And if it's right hand imagery, you see the left hemisphere ERD. And the ERS, I was wondering if anyone remember what ERS will appear, uh, in what conditions ERS will appear, the event-related synchronization. Can anyone remember, recall how ERS will appear? So when we start when we start executing the movement, then the ERD will appear, accompanying with the execution with the movement. And when we stop the movement, like we finish doing the movement, then the ERS will come up as a rebound of your frequency power of your power decrease by ERD. So it does not just rebound to the original level. It will rebound more, showing by the power increase as ERS, and then gradually getting back to the original level. Okay, so that's ERS. But anyway, when we talk about the left hand or right hand motor imagery, we can always expect to see a spatial difference and the power spectrum change. So let me introduce a data set of motor imagery. So this is a classic motor imagery EEG data set called BCI competition 428. So the name came from the an event long time ago, which is a BCI competition. And in the competition, they release a bunch of data set recording in their laboratory, uh, in a laboratory in Austria. So this is one of the category called 428. And this dataset contains 6 subjects, 2 sessions on different days, and 288 trials per session. So they have 9 subjects, human subjects, and each of them two perform 2 sessions on different days. So they came into the lab 2 times to do 2 recordings. And each recording contains 288 trials. That's multi-imagery trial. So let's look at the trial here. So this is the paradigm of the experiment. For each trial, the subject will first hear a beep sound and coming with the fixation cross on the screen that's at the center of the screen. And then there will be a cue showing what type of multi-imagery the subject is instructed to do in the following multiple injury session. So it could be either left hand, right hand, tongue, or feet. So once the subject see the cue, then after the cue disappear, the subject will have to imagine moving that part of the body for a few seconds, and then there will be a break for the subject to just take a break and waiting for the next trial coming in. So their forecast is left hand, right hand, foot, and tongue. So each class take each class takes 72 trials within a session, and they recorded 22 EEG channels. The layout is like this. So you can see they focus on the central area. You can see CZ is at the middle, and they kind of skip the some lateral channels of the EEG cap. So this is following the, the 30 channel montage, I believe. But they only use 22 EEG channels. And they also recorded extra 3 EOG channels. So if you recorded extra EOG channels, usually you want to use this EOG signals to do artifact removal from the EEG data. And the sampling rate is at 250 hertz, and the filtering of the recording was from zero point 0.5 to 100 hertz with a notch at 50 hertz, which is a power line frequency at Austria. So, and again, let's take a quick recap at the Fourier transform. For any time series, you can decompose it into the oscillation at different frequency. And let's also recap common spatial pattern. So we mentioned that this is good for separating EEG data of different classes, and it's particularly useful for classifying multi-imagery EEG because the if it's left hand and right hand, you will see that their distribution kind of overlap, but extended in different ways in the original data space. So make to maximize the separation of these two classes, the CSV is good because it can enhance the variance of one class while minimizing the variance of the other class. So it kind of project the data into two orthogonal uh, axes so that it can maximize the separation like this. And this cannot be done by LTA because you can see the center of each class is too close from each other. So it's uh, hard to increase the separation of their center point while minimizing their within within class variance。好，那这边我们就是介绍了这个一个 multi-imagery 的 data set。那这个是我们后面的一些 model 他们发展的时候所用到一个重要的 data set。那这边很快讲一下 Fourier transform，就是你的讯号都可以被不同频率的震荡所组合。那这边讲一下 common spatial pattern，因为它是对 multi-imagery 分类很重要的一个方法。那这边那讲这个是为了介绍 filter bank common spatial pattern。Okay, so filter bank common spatial pattern was the state of the art for multi-imagery classification. They won the BCI competition at the time, and it was developed by Kai Keng Wong and Kun Tai Guan uh, in 2008. So the method of filter bank CSP is to use a bunch of filters to filter your original EEG signal, multi-channel signal, into different subband. And then for each subband, they will uh, perform the CSP algorithm to estimate the spatial pattern for projecting the data to maximize the, the separation between classes. And then it will perform some feature selection. So these are some classic feature selection. People now use this less because we are in the age of deep learning. But in conventional machine learning, these are very useful to increase your performance. And these are the classification they use. They use a bunch of different classification, and at the end it will output with the class label of your EEG data. So it could be left hand, right hand, tongue, or feet. Okay, so this kind of shows the way of designing machine learning algorithm at the time. So you will use the property of your data. So here they have assumption, which is the best projection to separate different cases is different from one frequency band of EEG to another frequency band of EEG. So with this assumption, they first separate their original signal into multiple frequency band and calculate the CSP parallelly to get the spatial pattern for each frequency band. And then they try to integrate the information from the first two stage, and they also want to increase the performance. So feature selection is useful when you have redundant information at different features. And they use different classification probably because it's hard to justify in advance which classifier is the best for these EEG classification. So probably because of that they include many different kinds of classification and then integrate the prediction for each classifier. So this is like an ensemble approach to do this. 好，那这边就是讲一下这个 filter band CSP 的方法。这个是以前十几年前这个对于 multimedia 分类最好的做法。那它就是假设说你在不同的频带，你的 CSP 给你的 spatial filtering 其实是不一样的。所以他们就先用 filter bank，用一大堆的带通滤波器，将你的讯号转成不同 subband 的讯号，然后每一个 subband 呢，再各自去做 CSP，然后得到各自的 spatial filter，然后去做这个 projection。那出来的这些 feature 呢，就要做分类嘛。那他们会先做 feature selection 啊，一方面可能是说你前面这些资讯其实有一些重复的地方，那 feature selection 可以帮助你去减少这个累赘的资讯，然后截取比较好的资讯。那接下来这个 classifier 他们用了很多种，那可能是因为他们不确定哪一种最好，所以就都放进来用，然后再做最后的整合不同的分类器所预测出来的结果。那这个就是一种 ensemble approach，就是你把一大堆弱的分类器弄在一起用，然后来达到一个强的 performance。So this is a state of the art at the time, and we're very interested in the spatial spatial pattern and temporal pattern of EEG. So we can actually observe the spatial pattern gaining by CSP. So here, um, this is this is a visualization of the CSP spatial filters using the data PCIC 428. And in this example, there are only four frequency bands. That's from delta, theta, alpha, and beta. And this is the spatial pattern for each frequency band. So for the left hand, you can see. So for the left hand, the filters focus more on the right hemisphere. You can see the red color on the right, but they are slightly different across different frequency bands from left to right. And for the right hand, you can see the red color goes to the left hemisphere. And for foot and tongue, you can see the foot. For the foot cast, the pattern focus on the center around CZ, and for the tongue, it kind of focus on the center to the frontal. So you can see the red color here. So it's actually interesting to see this because we use machine learning techniques to learn from the data and to match the existing neuroscience knowledge we have. OK，那个这边是很有趣的一个地方，就是像这个 CSP 它训练出这些 spatial filter 的时候呢，那我们可以对它做 visualization。好，然后我们就可以看到说它的这个每一类，然后在不同 frequency band 它所找到的最好的 projection 长什么样子。那你可以看到 left hand 的话，它就着重在这个右侧动作区；那右手的话，就着重在左边的动作区；然后 foot 的话，它就着重在中间。那可能是因为两边都有左脑跟右脑都同时在用到，所以就有这样子的结果。然后舌头的话，可能就是比较偏前面一点。好，所以这就是不同 frequency，然后我们可以看到不同 frequency band 它从左到右，它其实有一些差异。 所以这个就显示出他们的这个假设，就是你对不同的 frequency band 可能要有各自的 projection，然后才会达到最好的 performance。Any questions so far? Okay, so from the conventional FPCSP, starting from about 7 years ago, people start developing CNN for EEG classification. As I mentioned, the the uh, the trend of deep learning started from the 2012, uh, where when the AlexNet significantly decreased the error of uh, image recognition using the ImageNet. And since then, people start focus on neural network again. And at the time, EEG investigators also tries to use neural network models to do the classification. Uh, but it was but there was a delay because in the beginning, people are concerned about the data amount we have for training a model because each data is not as abundant as other type of data. But some of the researchers still tries and eventually they create some nice CNN model for EEG classification. So the reason that CNN could be a good way to do EEG classification is because a lot of EEG processing is based on convolution operation. For example, the spatial convolution of EEG signal uh, can achieve the things like channel selection, reference montage, and artifact removal. So channel selection, if you want to use the information from part of the channels rather than all channels. So it's kind of using a filter, spatial filter to do this selection for you. And it can also do the referencing montage to extract specific features that people have been used for a long time. And you can do artifact removal because the artifact, some of the artifact can be separated using the spatial filtering. You can easily identify those artifact components using some unmixing matrix, and that's also spatial filtering. So so these are all good ways to extract features from the EEG as well as removing noise or artifact from the EEG. So spatial convolution is very important for EEG processing, and they all can be done by convolution. 好，那这边就是再回到之前我们有提到的，就是 spatial filtering 对 EEG 处理的重要性。那包括像 channel selection 或是这个 referencing montage，不管你是要做 referencing，还是你要取特定的 montage，这都是 spatial filtering。然后 artifact removal 也是建立在 spatial filtering 的基础上，你靠着这些 spatial filtering 去对你的 channel data 做一个 projection，得到这些 artifact 的 component，然后你就可以把它们移掉，然后得到一个断点讯号。Okay, any questions so far? So, so that's the first section of this class. I'd like to invite someone to get the bonus credit by summarizing our class in 1 minute. Any volunteer? So if there's no volunteer, I'll invite uh, Chen Zilin. Chen Zilin, can you hear me? Are you there? Chen Zilin, can you hear me? Uh-oh. And how about Tian Zhuying? Tian Zhuying, can you hear me? Hello? Can anyone hear me? Okay. Uh, all right. So we probably need a roll call after the break. So how about okay? Uh, Tu Shaoqi, Tu Shaoqi, could you do a summary for us? Just 1 minute. No，你也可以用中文，但是希望你可以就是很快的呃整理我们刚刚所讲的东西。哎，你可以讲话吗？嗯，好吧，那你就慢慢打讯息，我们可以再回来看，谢谢。OK，那就11点10分我们再回来。So Tu Shaoqi will give a summary by typing the chatting box, and uh, and let's go back here. Let's come back here at 11:10 after the break. See you later. Okay, welcome back. Uh, so, so let's look at the chat box to see the summary 涂少奇 gave us. 正交之后可以练得比较好。然后 spatial filter 那边可以看到左手对用右脑，右手跟左脑。Okay, so I believe the first sentence is about the CSP. The CSP will maximize the variance of one class while minimizing the other one. So it's actually projecting the two class onto orthogonal axis like this and to help your classification because now you have a better separability between classes. And the left hand imagery of left hand can be seen by the response that, like the power decrease at the right hemisphere and for imagery of the right hand you can see a decrease on the left hemisphere. So yeah, thanks for giving some of the detail in the lecture. So if I were to summarize my lecture in the previous section, I will say so. First I show I demonstrate I introduce the TensorFlow playground and I demonstrate model training using some of the data and create a model uh, designed by myself and to introduce how this can help everyone gaining experience of parameter tuning and model design. And then introduce the multi-imagery EEG pattern again. That's because I want to introduce the filter bank common spatial pattern, which is the conventional state-of-the-art algorithm for multi-imagery classification. And then I talk about interpreting some EEG patterns from machine learning methods like filter bank uh, common spatial pattern. So, and at the end, I touch upon the spatial convolution, the importance of spatial convolution for EEG processing. And that's pretty much what I went through for the previous lecture. So I hope you still have some memory, and because we will continue um, talk about um, the design of CNN for EEG. And before that, I'd like to do a quick roll call. So, starting from now, if you can hear me, if you're in a class, please put your okay. So, like following Tu Shaoqi, what Tu Shaoqi has done. So, type your student ID and name in the chat box starting from now. So that this can be done within 1 minute. So, everyone, please do it now. So, that's the roll call for today.